Hello everyone, welcome back to this course on reinforced concrete design. We are in week 3 and this is our first lecture. Now in the previous week we have discussed beam design, and if you recall we studied how to design a singly reinforced beam, then doubly reinforced beam and flange beams. Now after the design of beam against bending, we also discussed how to design against shear. Now, beyond that, there is one small issue left with beam design, and let us discuss that first before we go to the slab design, which is the main aim of this week's lecture. So, let us first start with the bond and detailing of this beam design. Now, when we cast a beam, as you can see on your screen here, we have rebars at the tension zone, and then we also have concrete which is giving the shape of this beam, having a width B and effective depth D. Now for a rectangular beam we actually have rebars at the bottom. For this case, to take tension, as we all know, concrete is weak in tension. We also have additional rebars we do not consider in singly reinforced beam, but these rebars actually hold the stirrups against shear force. And then together they give a shape of a rectangular shape of this beam. Now, when we pour concrete, before that, first we make a formwork here, a rectangular formwork, and then we place the steel. So this is the formwork. Then within the formwork, we first place these rebars, and then once it is done, we pour concrete here, and then we cure it for 28 days, and then we remove this formwork, this shuttering, and then we get the shape of a rectangular beam. Now once we get this rectangular beam after removing the shuttering and then apply the load, as you can see here, then this concrete and the rebars inside the concrete, they should behave monolithically. And that's the reason we should have sufficient bond between the reinforcement and the concrete, so that there is no relative deformation. So if this is a beam spanning over simply supports, and then the moment we apply a load here, it will start bending like this. Now if there is no proper bonding between concrete and steel, then what will happen? There may be a slip between these rebars, as you can see here, and the concrete surrounding it, and that may actually lead to failure. And that's the reason when we design a beam, there should be sufficient bond, and the bond strength we have to check. Now for this purpose, proper detailing is required for full utilization of member strength without any premature failure. As we progress in this course, you will see how we can go for a proper detailing. There are certain aspects of these tensile rebars that we will discuss one by one, but the type of bonds that we are going to discuss in this lecture are of two types. The first one is the bond against flexure, and then the anchorage. Now let us take the first one, which is flexure bond. Now when this beam bends, because of this variation of the bending moment, so if you take a section at 1 and at 2, so if the bending moment here is M, obviously here it is M plus dm. Now due to this variation of the bending moment along the length of the reinforcement, we need to provide sufficient bond against flexure, because you can see between these two sections which are dx apart, there is a difference of dm bending moment, which we can convert into a force acting on the rebars. So let us see how we can quantify this force, and then this force will give us the necessary length required for this bond between reinforcement and concrete. So let us consider two sections, as I said, dx apart, and at section 1,1, that is the first one at a distance x from the left end of this simply supported beam, the moment at this section we can calculate T is the tensile force on the rebars. You can recall from our beam design that multiplied by the lever arm is the moment capacity or MR at that particular section 1,1. Similarly, at section 2, we can calculate the total moment of resistance from the tensile force. At this section, we have T plus dt times LA is basically M plus dm. Now, from these two expressions, we can find out the quantity dm, which is nothing but the change in the tensile force over the rebars times the lever arm, right? Now, this is the additional force acting on the reinforcement between a section 1,1 and 2,2. As you can see here, we have T at one end and T plus dt at the other end. They are acting over a length of dx, and due to the variation of bending moment between section 1,1 and 2,2, which are dx apart. Now, obviously, as you can see here, this is the bond between the rebars and the concrete here, right? Now, if we can quantify this bond strength, we can actually correlate that with the force or the additional force dt between the section 1,1 and 2. How to do that? We have the reinforcement having a diameter of phi. Now, if we apply the equilibrium along, say, this direction of x, then what we get? We have T minus T plus dt minus tau is the stress acting over the surface area, and for that we have pi times d, or 2 pi r is the perimeter times the number of bars you have times dx is the total force. Obviously, all of them will maintain equilibrium if there is no slip in between, and therefore this will be equal to 0. If that is the case, what we get is the change in this force over the rebars between the section 1,1 and 2,2 is nothing but tau times n pi phi times dx. Now, we have already evaluated what is the quantity dm in terms of dt. It is dt times LA. So, what we get is dm dx is nothing but tau times n pi phi times lever arm. Now, from this expression, we can get the expression of tau, as you can see here, which is dm dx multiplied by 1 by, in the denominator we have n pi phi times LA. Now, this quantity dm dx between section 1,1 and 2,2, we know this is nothing but the shear force acting. So, ultimately what we get, tau is V by, in the denominator we have n pi phi times LA. So, that is the expression of bond stress, right? Remember, it is against flexure between section 1,1 and 2,2. Now, the value of tau should be less than the permissible bond strength So the design bond strength we get again from the code, that is IS 456, and the clause is 26.2.1.1, and from there we get the design bond stress tau BD for different grade of concrete. Now this tau BD, for example, if we consider M25, it is 1.4 Newton per millimeter square. If it is M35, tau BD is 1.7 Newton per millimeter square. And for M40 and above, the value is fixed at 1.9 Newton per millimeter square. Now, one thing to be noted here, that these values given in this table, they must be enhanced for HYSD bars. So these values are for plain rebars, for example, say Fe250. Now these plain rebars, when used in case of beam design, they develop at the surface, so if you, the bond stress tau. Now the moment we use HYSD bar, these HYSD bars, they have these helical ribs over the surface, as you can see here, and because of that, obviously it offers more bond stress against flexure. And the code says that in case of HYSD bar, we should enhance the value of tau BD by 60%. Not only that, in case of compression, we can further increase this value by 25%. So these are the codal provisions we have. And now if we take an example of a design bond stress for bar of Fe415 under compression in M30 concrete, we can calculate tau BD. How? We have Fe415 bars. So this is a HYSD bar. Obviously for that we can increase 60%, and we use this bar against compression. So for that we can enhance another 25%. Now we have M30 concrete here. So for M30 concrete, tau BD is 1.5 Newton per millimeter square. So for this design problem, tau BD is 1.5 for M30 times 1.25, we have 25% enhancement because of compression, and then because we use HYSD bar, another 60% enhancement of this value. So ultimately for this case, we have a tau BD which is 3 Newton per millimeter square. So you can see we can find out the bond strength tau BD as per codal provisions and different grades of concrete and different types of steel. Now let us go beyond. So we have another type of bond, and that is anchorage. What is that? It develops around the bar to provide proper anchorage so that reinforcement attains its desired stress. Now just imagine we have this cantilever beam, and then for a cantilever beam, if this is a cantilever, the moment we apply a load here, it deforms like this. Now when we provide rebars, obviously if this is the column face, then the top face is under tension, and therefore the main rebars against flexure we should provide here on this face. Now the question that we are going to answer is whether we stop this rebars here at the face of the column or it should go beyond, right? Because we need proper anchorage, we have to actually go beyond, otherwise we cannot provide. If we provide rebars from here, there may be a slip and it may fail. Now as you can see, this is the anchorage length. So over this length, if we provide the bar which continues over here, then over this length from the face of this column, the anchorage between the concrete and the rebars develop. This anchorage length, say, is L, and we have to design that anchorage length. How do we do that? For that, we again have to define this FST, which we will do it in a minute. And based on that, we actually have to design the sufficient anchorage length for this problem. So overall, what we get, the take-away point is L is provided in this type of situations for anchorage of reinforcement only. So bond stress around the reinforcement in this length is anchorage bond and not the bending moment variation in this portion, because over this section there will be no variation of the bending moment, but still we need this anchorage to protect the reinforcement from failure. Now in case of bond failure, most economical way to make it safer is by providing more number of bars, which is obvious, because if we have more number of bars, then we will get more surface area, and more surface area will definitely develop more bond strength. And how to provide more bars? We can provide smaller diameter. Instead of less number of larger diameter bars, if we provide more number of smaller diameter bars for the same amount of steel at a particular section, then what we get, the benefit is that we get more bond strength. Okay. Now for this anchorage, we have a dedicated clause, as you can see here in IS 456, it is 26.2.1. Now, for development length, again, let us solve a problem. So the minimum length of reinforcement required to be embedded in concrete for development length will have permissible stress as 0.87 Fy. Now obviously if we have a diameter, as you can see here, that is the bar diameter, so pi d square by 4, that is the cross sectional area, times FST, that is at the end of the bar, is equal to tau BD, that is the bond strength, times pi d, that is the perimeter, times LD is the total force developed. So we can calculate LD, which is FST times phi, that is the diameter of the bar, divided by 4 times tau BD. Now FST we get, as I have already explained here, is 0.87 Fy. So ultimately the development length is 0.87 Fy times phi divided by 4 tau BD. Now if we consider this example where we compare the development length of the bar when we use Fe250 and Fe415 of same diameter and embedded in the same concrete. So we use same concrete for these two different types of bars where the diameter remains same. So for Fe250, obviously LD, as you can see here, it is 0.87 Fy times phi is the diameter of the bar, which will remain same. The only thing is going to vary is Fy. So the first case we have 250. So we'll use 250 here, and in the denominator we have 4 tau BD. So ultimately if we put this value 250 here, we get 54.37 times phi divided by tau BD. Now if we repeat the same exercise for the different steel, which is Fe415, what we have here, as you can see, is LD is equal to 0.87 Fy, that will remain same, but in case of Fy, instead of 250, we now have to put 415 times phi, that is the diameter of the bar, and in the numerator we have tau BD, but because we use HYSD bar, for that we can enhance tau BD by 60%. So that's why we have 1.6 times tau BD here. So ultimately what we have here is 56.41 times phi by tau BD. So this part is common for both of them. So effectively what we have, a factor 56.41 here in case of Fe415, which was earlier in case of Fe250 is 54.37. So obviously for HYSD bar, the development length LD is higher than mild steel. Okay. Of course, for the same diameter and grade of concrete. Now, when we design rectangular cross sections, or for that matter any other cross section, sometimes we provide bars in a group. For example, we have, say, this is the bar, this is one way. Now, we can also provide in a different way. For example, the central bar, we provide two smaller diameter bars, but we group it together. And we can have different combinations. As you can see here, two bars, it may be of same diameter, may not be of same diameter, but two bars are bundled together. Then we have 3 bars and 4 bars. Obviously, these are special cases, normally not recommended, because the moment we provide 2 bundled up bars, we will not get the complete surface area, and therefore individual bar, if they behave as a single unit, will have sufficient bond strength developed over the complete surface area. However, in case of bundled up bars, because this surface area, for example, this region is common, that will not take part in bond strength, and therefore we need to increase the LD to get the same value when we have a single bar. Similarly, if we have 3 bars, we have to increase it 20%, and for 4 bars, we have to increase it by 33%. And this is as per clause 26.2.1.2. And definitely, we have to calculate bundled up bars based on this increased development length, and we have to provide that sufficient development length at the end so that there is no bond failure against flexion. Now, the difference between development length and anchorage is that the value of stress that we use. In case of LD, we use 0.87 Fy, and in case of anchorage, we use 0.6 Fy. Now, let us see different bond failure mechanism. So the first one is the breakup of adhesion between bar and concrete. That is the first type of or common type of failure. So if we have beam like this, and if we have a reinforcement here, beam is simply supported. Then the adhesion between this bar and the surrounding concrete may fail, which may lead to bond failure. The second type is crushing of concrete in front of ribs of bar. So we have this type of helical ribs we have. So just in front of these ribs, just imagine these 2 ribs in between these concrete, this may be under compression. So there may be a failure of this concrete in front of the ribs of the bar, and that may lead to a bond failure. Then, as you can see, this longitudinal split of concrete along the reinforcement, this may also lead to bond failure because that will offer insufficient bond stress developed surrounding the bars. So these are the 3 different types of bond failure mechanism very often we encounter. Now at the same time, what are the factors that enhance bond strength? Obviously higher grade of concrete. You have seen if we use HYSD bar instead of plain bars, we get better strength. Smaller diameter bars, because smaller diameter bars for the same amount of AST will offer more surface area, and therefore we'll get more bond. Then more nominal cover. So if we have very less amount of cover, then what happens? The strength of concrete between these 2 planes, one is here, another is the outer surface. Because we have a less cover, the concrete strength is not developed. So more nominal cover will actually give sufficient strength around these bars, and therefore we'll get more bond strength. reduce spacing of stirrups. So if we have shear reinforcement and if we have closer stirrup, then also we can enhance this bond strength. Now, what are the different ways of providing anchorage? This is as per clause 26.2.2. We can provide development length. We can provide bend or hook. I will just discuss this in a minute. And we can also provide mechanical anchorage. I will show you what we mean by this mechanical anchorage. Okay. Now, let us see the different type of anchorage by providing development length. Now, as you can see here, we have a cantilever beam, and then on the top face, we have this tensile reinforcement. Now, we have already explained that in this case, we should not stop at this column face, but we have to have sufficient amount of embedded length so that it can develop sufficient length for bond stress, right? Now, as you can see here, this entire reinforcement, we can split it into two halves. One is here and another is there. In both the cases, the length should not be less than the development length that we can calculate. The procedure I have already explained. Now, in case of, you see this arrangement, in case of the geometry of the beam, we do not have sufficient length here, so we cannot provide it in a straight form. In that case, what we need to do, we have to bend it, but we have to provide this length sufficient enough to develop this bond strength. For that, again, this length should not be less than actually the bond length that we can calculate for this flexure problem. Now, one point to be noted here, in no case distance between the section of permissible stress of steel and the end of steel should be less than LD. So this is the point to be noted here, and accordingly we have to provide sufficient amount of length so that we get proper anchorage. Now, when you come to this corner, as you can see here, although we bend the bar in 90 degree here, but at this corner we cannot provide a perfect 90 degree because it has some diameter, and that's the reason we have to provide a bend there, right? As you can see here at this corner, there is a bend which is explained here. So now, for every bend we have or every hook we make, we get anchorage, and the equivalent anchorage is equal to 8 phi in this problem where we have 90 degree bend, and for that, as you can see, this is the radius of the bend. Now, for mild steel, this R is twice of phi. Phi is the diameter of the bar, and for HYSD, this R actually 4 times the diameter of the bar, and that means for HYSD bar, if we provide, the size of this bend will be bigger because R is more, which is 4 phi. And then, as you can see from this geometry, from this point we start the bend. At this location, we come to this 90 degree bend. And then beyond that, we have to provide another 4 phi to develop sufficient anchorage. Now, when we have 180 degree bend or hook, then for this problem again, the R for mild steel is 2 phi and HYSD it is 4 phi. Then at this point, we start the bend. So first we have 90 degree bend. So from this point onward, we have another 90 degree bend which stops here. So together these two, we have 180 degree bend, and beyond this point again we should have 4 phi for sufficient anchorage. Now obviously we have to check this LD, and based on that we have to take a call. So if this is sufficient enough, so we can stop here, or otherwise we have to provide sufficient length. And in case of anchorage, as you can see here, the equivalent anchorage length is 16 phi. So we can provide here a 90 degree bend, as you can see, or we can also provide a hook of 180 degree. If we obviously provide hook of 180 degree, then the anchorage strength will be more compared to 90 degree. So the point to be noted here, for each 45 degree bend, equivalent anchorage of 4 phi is taken, subjected to a maximum of 16 phi for standard. right? Now, equivalent anchorage of bond and hook is not considered for reinforcement under compression. Okay. So, these are all about anchorage. Now comes the mechanical anchorage. So, as you can see on your screen, we have this simply supported beam where we have these rebars. Now, in case if we cannot develop sufficient anchorage length here at this end, then what we can provide is a mechanical anchorage. So, we have anchorage here, as you can see. So, it is a form of a plate, and then we can screw it this rebar at the end, and then thereby we can actually provide a mechanical anchorage at the end. And obviously this anchorage should have sufficient strength to provide sufficient bond at the end so that there is no slip between the rebar and the concrete. Now when we talk about stirrups, as you can see here, the stirrups is formed by bending a bar. Say if it is a 8-phi bar, then at this location we start this bend, and then there is a length of 8-phi after a 90-degree bend. Sometimes we provide a full hook, as you can see here, which provides a 6-phi of anchorage length, and sometimes we can also provide this type of hook which offers a better anchorage at the corner. If you have a bar here, obviously this bar is fully anchored inside, and for this we should also provide after this bend this 4-phi, as I have already explained. And the clause is 26.2.2.4 in IS 456. So this is the type of stirrups that we use for sufficient anchorage against shear. Now, there is another issue. So, say we have a beam which is simply supported. Now, obviously, the bending moment diagram for this beam is for UDL something like this, right? Which is maximum at the middle. So if we go towards this two ends, obviously the bending moment requirement is much more less, and which is ultimately 0 at the two ends because of simply supports. Now, if we design this beam against this value of applied moment, then obviously the amount of steel we estimate we provide here, but as we go towards the end, the requirement of steel is less. So after a certain point, we can reduce the amount of steel, and that is what is done using splicing. Now, there is another issue. Sometimes we have, say, a large beam and then we have, say, intermediate supports. So we need to provide, say, this rebars, and obviously for these type of beam, we'll have hogging moment at the support. So for that, we have to provide rebars at the top. But as we go towards the two ends, because of the simply support, their requirement of steel at the top face will be less. So we can reduce the bars. So you see, we can reduce the bar, and not only that, if we have a large beam, then in between, we often need to lap two bars because we may not get a single bar of that sufficient length. The question is what we should do in those cases and how we should place the bar, because if we have a lap here, so that means we have one bar here and another bar coming here, because we do not have a single bar of sufficient length. So over this length we can lap it. Now, this length is called the lap length. And the clause in IS 456 is 26.2.5.1. And for bar diameters greater than 32 millimeter, lapping is not actually desirable. Now, when we provide these type of lap length, the code says against bending, we should provide a lap length of maximum of these two. So LD, that is the development length, we can calculate at the section where we provide this lap. Then LD and 35, that is the diameter of the bar, maximum of these two we have to provide as the lap length. If it is under direct tension, then maximum of twice LD and 35 should be provided as the lap length. And in case of compression, the maximum of LD and 24.5 is what we are supposed to provide as the lap length. And for unequal diameter bars, because we can provide lap over unequal diameters, in that case lap length must be calculated corresponding to smaller diameter bars, because that will dictate this length. So we have to find out smaller diameter in the unequal diameter bars for lapping. Then based on that, we have to calculate the lap length, right? Now, sometimes we also provide welding of bar, but again, it is not preferable, because during the process of welding, what happens, the cross section of the bar may be affected, and that is not desirable, and that's the reason we prefer not to have. So sometimes for large diameter bars, we can provide this welding, but in those cases, we have an alternate solution. So we have one bar here, another bar there, and we have a coupler, that is a connector between these two bars. So using this coupler, we can connect these two bars, and which offers a better option compared to welding. Because of welding, if we have a surface and then if we apply welds here, this surface may get reduced because of the welding, and that is certainly not desirable, because in that case we have lesser amount of effective area of the steel. Now, one point to be noted here, not more than 50% reinforcement should be spliced at one location. So if we have a case of splicing, then half of the amount of steel provided at a particular section should be lapped, and then we have to have another location where we have the remaining steels, they are lapped. Okay. That means they have to be staggered, and the distance is 1.3 times the lap length. So that is the recommendation of the code for this providing lap length of the bars. Okay, now you can see we started with this example of a simply supported beam where we have the maximum bending moment at the middle, and as we go towards the end, bending moment reduces. You can see here we have M1 is the bending moment at the middle, and M2 are the bending moment at these 2 points as we go towards the end. Obviously, the steel requirement at this point where we have M2 is much less compared to M1. Now, splicing is not recommended at the location where bending moment is more than 50% of the capacity of the section. So, this is another point to be noted. Now, for this clause, actually 26.2.5 tells us first you find out the bending moment over the length of this beam, and then based on the value of the bending moment, you first check every section what is the capacity, and if the bending moment is more than 50% of the capacity of the section, then the splicing is not recommended. Now the question is, as we progress towards the end, the moment reduces, so we can reduce the amount of steel we provide towards the end just because less amount of applied bending moment, and that can be achieved by curtailment of reinforcement. So we have the steel which is maximum at the middle, Then as we go towards the end, obviously we can reduce some number of bars. So if we have, say, a cross section where at the middle, based on the value of the bending moment, say we have 4 bars, and at the end, say at this point here, we can reduce 2 bars. So at the middle, we'll have 4 bars, but at this section, say, let us mark it, say 2, 2, as opposed to 1, 1 at the center. So this is for section 1, 1, and then at 2, 2, what we can do, we can reduce 2 bars. So we'll take the 2 extreme bars through and we'll reduce the bars in between. So that is the section at 2, 2. So bars under flexure are deemed to be curtailed beyond the point it is no longer required, and that is as per 26.2.3. However, curtailment should be done after satisfying the codal provisions. What are they? The distance between the theoretical cutoff point and the actual cutoff point should not be less than d or 12 phi, whichever is greater, except end of simply supported or end of cantilever. Now, say this is the theoretical point of curtailment here. Then what we have to do, we have to go certain distance beyond, and that is the actual location of curtailment. So we have 2 things, theoretical cutoff point and actual cutoff point. Now, the distance between these two should not be less than d or 12 phi, whichever is greater. So we have to see the effective depth of the beam and diameter of the bar, 12 times of that. These two values must be checked, and the greater values will be what is provided here. So this is theoretical cutoff point and this is the actual. As you can see here, so we have in this example, say we have 625 diameter bar at the middle. As we go towards the ends, we can curtail. So 425 bars are taken at the end and 225 bars are reduced. So at this point, we have theoretical cutoff point. However, as per code, d or 12 phi, whichever is greater, we have to take it more, and then we have to provide an anchorage here. So we bent up it slightly and that will provide an anchorage here, and that's how we provide steel. So this detailing you have to follow when you go for curtailment. Now you can see here in this cantilever, so we have actually, this is the point where we can curtail the bar, because beyond this the bending stress is very less, but we do not curtail it here. We take it inside and we provide sufficient amount of length here so that we develop sufficient anchorage, as I already explained earlier. Now, in case of simply supported beam, as you can see here, if the support width is here, as you can see, say B support, then we define the support point at the center line of this support. So this is the point where we have the simply support. Obviously, at this point, the bending moment will be 0. Now, the question is, we cannot stop it. That is the theoretical cutoff point. But we have to go beyond this theoretical cutoff point. So either d or 12 phi, greater of these two we have to provide. If we can provide in a single length, then otherwise, if not, we have to bend it and we have to provide that sufficient anchorage. Now, flexural reinforcement should not be terminated in tension zone unless any one of the following conditions are satisfied. The shear force at the cutoff point ACB should not exceed 2/3 of the shear capacity of the section. So if that is the case, we cannot propose this termination of the reinforcement. The second point to be noted here, if the shear force is more than 2/3 of the shear capacity at ACP, then excess shear stirrups are provided along the terminated bars for a distance of 0.75 D from the ACP. So we provide additional stirrups there up to which distance? 0.75 D from the ACP. Okay. So as you can see here, we provide actual cutoff point here. So over this region, we have this additional shear reinforcement. And the distance is 0.75 D. Now for 36 millimeter or smaller diameter bars, the continuing bars should provide at least double the area required for flexure at a cutoff point ACP, and shear force should not exceed 3/4 of the shear capacity. So these are the different codal provisions to be noted while we propose curtailment of bars. And I have already explained, at the middle we have large number of bars as we go towards. So this is the theoretical cutoff point, but we have to go beyond that, and then we ultimately take this 5 bars and curtail 2 bars of 25 diameters. And for that again, accordingly, we have to provide additional shear reinforcement based on the different capacities at the sections. Okay. Now, let us again revisit this curtailment of reinforcement against flexure. So for tension, so we have sagging positive and hogging negative. So at least 1/3 of the positive tension reinforcement at simple support and 1/4 of the positive tension reinforcement at continuous support should be extended along the same face of the member into the support at a distance not less than LD/3. So again I repeat, as you can see here, we have a curtailment here. Then what it says, at least 1/3 of the positive tension reinforcement at simply support and 1/4 of the positive tension reinforcement over the continuous support. So here we have continuous support and here we have simply support. So in that case, the bars here, you see this length embedded over this support, it should not be less than LD/3. Right. And then accordingly, we have to provide the curtailment scheme for the simply support as well as the continuous support. Now, at simply support and at the point of inflection or contraflexure, positive tension reinforcement should be limited to diameter such that the following expression must be satisfied. So you can see here at this point, the tensile phase actually changes. So here at the middle, we have this bottom side which is under tension. At the support, we have top phase because of this hogging moment which is under tension. Then what we can do, the amount of steel provided at the middle, we can actually reduce. But if this is the point of contraflexure, then you see this is the actual point of curtailment, and this L0 is the maximum of these two, D or 12phi. So from the point of contraflexure, we have to provide this L0 and then we can provide this. And that is for continuous support. For simply support, I have already explained. So we have to find out the center line of the support, and from that point, we have to extend this up to L0. Right. Okay, so if we just sum it up, at the simply support, we have to have this LD development length is less than equal to 1.3 M1 by V plus L0, where LD is the development length and MR is the moment of resistance of the section at mid of the simply support and point of inflection, whichever is appropriate. V is the shear force at the middle of simply support or the point of inflections. And L0 for simply supported end, anchorage beyond the center of the support, including equivalent anchorage value of bend or hook and mechanical anchorage, right? For point of inflection, D or 12 phi, whichever is greater, I have already explained with diagram. So for point of inflection, this LD is less than equal to M1 by V plus L0. Okay. Now, we have this 1.3 factor, that is 30% increase of M by V value is used for simply support end to account for confinement of concrete due to compressive support reaction. Now let us see for the negative bending moment, which is hogging at the continuous support. Then we can calculate this still based on the requirement. So this value of M applied. So for that we can find out the amount of steel here that is required. Now as we go towards the midspan, obviously the tensile phase is here on the other side. And this point is the point of contraflexion. So we can theoretically curtail this bar here at this point, but again what we have to do, we have to provide some additional length. And what is that? D or 12 phi or L clear, that is the clear span. So from this phase we can find out the clear span divided by 60, whichever is greater. So that is the length for the rebars following this condition. So at least 1/3 of the total reinforcement provided for total negative moment at support should be extended beyond the point of inflection up to a distance not less than D or 12 phi or 1/16 of the clear span, whichever is greater. So we find out the amount of reinforcement for this hogging moment here. Then we identify this point of contraflexion, which is the theoretical cutoff point. Beyond that, we provide additional length, which is mentioned here. Similarly, on the other side, depending upon the clear span on this side, we have to provide this sufficient length, as you can see here. So that is the scheme we have to provide, and accordingly we can curtail the bars. So now let us take an example. So for this example, so check for bond of simply supported beam and assume two 32 phi bars are curtailed before support. So what we have here, we have 4 32 phi bar plus 1 16 phi bar. So altogether we have 5 bars here. Now out of that, 2 bars will be curtailed near the support. The B of the beam is 400, D effective depth is 800. We have this load is given, L effective in this case 11.45, and then we have support width also given. Now for this condition we can find out LD, which is 0.87 Fy divided by 4 tau BD, that we have already explained. And because we use M30 concrete, so for M30 concrete we have, this is the value of tau BD, which we can increase by 60% because of the HYSD bar used in this problem. So we find out the development length, which is 1450 millimeter. Now M1, that is the moment of resistance of section at mid of the simply supported beam, is with 2 32 phi bar plus 116 phi bar. The reason is we curtailed 2 32 phi bar near the support. So under these conditions, we can find out the location of the neutral axis using C equal to T. From your beam design, you can recall this. And this formula is familiar to us. We have 0.36 FCK XU times B is equal to 0.87 Fy times AST. So we know AST, and from this equation we can find out XU, which is 182.2 millimeter. Now once we find out XU, we can find out M1, that is the moment of resistance for that section, and it is 0.36 FCK times XU times B, that is the compressive force, times the lever arm, which is D minus 0.42 XU, which comes from our previous discussion. So if you put all these values, we get M1, that is the moment of resistance at that particular section, is 569.45 kilonewton meter. Now the shear force at the support is omega u, that is the UDL times L effective divided by 2, and the shear force is 332.76 kilonewton. Now if you use this expression LD, it should be less than 1.3 M1 by V plus L0, which I have already explained. So what we have to provide is L0 is minus 774.68 millimeter. Now this negative value of L0 represents no requirement of extension of reinforcement beyond the center of support, because this is negative. If it is positive, so that is the value of extension that we have to provide. So you can see for this curtailment, we can actually provide the scheme of curtailing two 32 diameter bars. Now you can see the arrangement of bars at the end. So in addition to previous criteria, reinforcement must extend into the support for a distance of LD by 3, that is not less than this distance. So how do you provide? LD by 3 is 483.33 millimeter. So we have to provide sufficient length here, and for that we cannot extend it this way because we have to provide clear cover here. So for that, how do you estimate? We have LD by 3 is equal to x1. As you can see, this is x1 plus 8.5 plus x2. So we have a 90-degree bend. So here we have, because of this bend, additional equivalent length, if you recall. So we have 90-degree bend, R is equal to 4.5 because we have used HYSD bar, and that's why we have this 8.5 here. So LD is equal to B, that is this width, minus the clear cover. We have to provide this clear cover here, as you can see, minus the clear cover, minus 5.5. So which is here. Then that is x1 plus 8.5 plus x2. Now if we put the values of LD by 3, which is 483.33, and here B we know that is 400, clear cover is 45, and then diameter of the bar is 32, so 5 times 32. What we can calculate is x2, so that is the value of x2 we have to provide here. So this longitudinal reinforcement for this simply support, we bring it up to the center point, and then beyond that we provide up to this X point here, and then we can stop this reinforcement as per our codal provisions. Now for this L0 greater than 0, LD by 3 and B of above expressions are replaced by L0 and B by 2. So that is obvious, because if L0 is greater than 0, then we have to provide L0 here, and so for that L0 is equal to B by 2 minus clear cover minus 5.5 plus 8.5 plus x2, and then we can accordingly find out how much distance we have to provide. So that is the x2 here. So you can see how we can provide sufficient bond length and the anchorage so that there is no slip between the steel reinforcement and the concrete. This is very important, and we have also discussed where we can curtail the rebars, because along the length of the beam bending moment will vary, and therefore if we design the section based on the maximum bending moment, as we move along the length of the beam the bending moment will vary, and accordingly we can curtail the bar, but we have to provide sufficient length of the bar between the theoretical cutoff point and the actual cutoff point. And all these different code clauses we have to follow when we go for the detailing of rebars. Otherwise, in our previous lecture, we designed against flexure and shear, but this is extremely important because if you have a continuous beam, say for example, then the nature of the bending moment changes from midspan to the support, which is sagging at the midspan generally and then hogging at the support, and accordingly we have to provide the detailing of the rebars. So these are the points which are extremely important. Just go through these derivations, go through these notes, and if you have any doubt, do let us know, then we can clear your doubt. However, once you go through all this and you can provide a proper detailing of reinforcement in case of beam design. So do let us know if you have any query in our email provided or the open sessions that we are going to have. Thank you very much.